Hello, everybody. Thank you for joining us today for another TELOPS webinar. My name is Chris Giesecke, and I am a field application scientist with TELOPS Exosense. I'll be acting as your host and your pilot for today, and I am very excited to also have with us our guest speaker, Hossein Aguilantes. Hopefully I pronounced that
Hello.
properly.
Yeah, it's correct. Thank
Um,
you.
just wanted to quickly get a few housekeeping things out of the way before we get into our presentations today. First, I want to let you all know that this webinar is being recorded, and a link to download or review the recording will be sent in a follow-up email to all of the registrants. Okay, and we also encourage questions from the audience. So if you hear something during today's presentation that sparks some interest, or you would like some more information on, or have any questions, please feel free to use the questions box in the GoToWebinar platform. What we'll do is we'll reserve kind of about like 15 minutes at the end of the presentation to answer some of those questions live. And then what we'll do is in our follow-up email, we'll provide written answers to those questions. So if there's any that we aren't able to get to during the Q&A, we'll make sure to provide written answers or written response to those answers when we send out our follow-up email. Okay, I think, let's see here. So I think we can go ahead and get started. Um, so our presentation here today is focused on some really interesting aspects of high speed, high energy material testing, in which we'll talk briefly about that before our speaker presents. So I'll give a little bit of an introduction just from our side on the TELOPS Exosense side. That way, if anybody isn't too familiar or isn't quite familiar with some material testing and infrared imaging, we can at least get some sort of a background on it. Okay, so let's go ahead and get that started. All right. So today we're here, thermomechanical relationships and materials under tension or strain. Here's an outline for today. So I'll again provide an introduction of TELOPS Exosense, include some of our cameras and our products, provide an applications overview, infrared imaging and experimental mechanics before, before I then turn it over to Hossein, and we'll hear him go through his presentation. And then at the end, we'll save some time for some Q&A. So TELOPS, which is now an Exosense group, okay, we were started in 2000 in Quebec City, Canada, and we now employ over 100 people. We have established ourselves as kind of a world leader in thermal infrared imaging, scientific infrared imaging instruments and solutions. And we recently joined the Exosense group, a larger group of imaging companies. We offer innovative solutions for aerial methane leak detection and quantification now. And we have the privilege of working with a new member of the group, LR Tech. These are some of the products that we offer. Okay, everything from when we first started our hyperspectral cameras, the high spectral resolution cameras, through our regular broadband cameras. But we also have multispectral cameras, which is time-resolved multi-channel imaging through 8 different filters and a rotating filter wheel that can allow for simultaneous capture of 8 different filters observing the same scene. And then the cameras that we're more or less going to be talking about today, a high dynamic range camera. I'm going to bring attention to this because of something I recently heard in a presentation for DIC. But this camera allows up to a 900 degrees Celsius range, scene range within a single exposure time. Okay, then we have our high performance fast cameras, of course. These are cameras for high speed imaging. And if we window down, we can get up to 100,000 frames per second with our fastest camera. And then we have these new entry level Radia cameras, which we'll also talk about today. These are smaller, more compact, low swap size, weight, and power cameras that we think could fit very well into this realm. Some of our main applications here, ballistics, combustion, IR signature, gas detection, cold spray, it's an evolving one. Of course, experimental mechanics, which we'll be focusing on today, some additive manufacturing, NDT or non-destructive testing, mineral identification, and fire research. So these are not all of the applications that our cameras are used for, or that we use our cameras for, but these are some of the main ones that they typically get used for. So we'll first start with our high-speed cameras because experimental mechanics and high-speed imaging can go hand in hand here. And as I mentioned earlier, our fast M3K is our fastest camera. If we look in this box, we have our fast M2K and our M2K UD. But our fast M3K is in a full frame window at 320 by 256 pixels. You can sub-window that down to 100,000 frames per second. Then our fast M2K in a full window reaches about 2,000 frames per second and can be windowed down fully to that 90,000 frames per second. And of course, we have some lower speed cameras as well, if maybe that are a little bit lower in cost, or if you don't necessarily need that super high frame rate. So in materials testing, experimental mechanics, materials under stress will provide a thermal response. And so we can use infrared imaging to capture that thermal response and that energy transfer. So there's a few examples here of data that has been collected with our cameras. And we're able to observe things like thermoelastic cooling and heating. So I'm going to play this video for you right here, and we'll be looking at this rectangle, which is our region of interest. And when we play this video, you can see if we follow this graph that we have a pretty distinct thermoelastic cooling effect right before we start to get into plasticity. So the elastic zone, where the material undergoes cooling right before we see a temperature rise. And that temperature rise is the thermoelastic heating, which is the onset of plasticity and allows us to track damage evolution to a fracture point. Okay, and over here on the side, you can see we use that to be able to experimentally quantify those two measurements. And we can also look at this in order to visualize rupture point displacement and propagation of localized strain. So we're going to play this video here. This is another test, and we have a line profile that goes through the sample like this. And if we look over at this line, the line profile temperature plot, we can clearly visualize the propagation of this localized nuclei as it evolves up to a fracture point. So infrared imaging is really good to be able to capture those processes. And with those, you most likely use some sort of a high-speed camera in order to obtain those measurements. Then also we have here a split Hopkinson bar test. This was done with an M3K and windowed down with using a frame rate of 43,000 hertz. So 43,000 frames per second for this test. The playback speed is much slower than the actual event itself. at 0.0004 times, but we can also see the information that is provided by the infrared camera during the split Hopkinson bar. Again, we can see the propagation and we can see the thermal energy response within this video and during this test. We have down here, so that was with the M3K, what it looks like. It's also been used with one of our high definition cameras, the M200 HD. And even though that's unable to achieve the frame rates that the M3K is, it's still able to provide some detailed thermal response at a little bit higher resolution. And we can see a higher definition from that camera during this particular test as well. Then the one below it is just a contrast enhancement, which allows you to kind of, a feature in our software allows you to look at the sample or the test or the thermal response in a different way. And sometimes it brings out more information than what you originally see. Okay, there's also the ability to integrate thermography or infrared thermography with digital image correlation. You can use DIC to take the mechanical portion of it, and you can take infrared imaging to capture the thermal response of it. You can take the temperature data points, so the pixels, and you can map that onto a DIC points grid. And this enables us to find a coupled relationship between the mechanical strain and thermal dispersion during the testing of a particular sample. This kind of gives us a better understanding of the spatial-temporal aspects of localized strain and what's happening during that process. And also allows us to better understand the thermomechanical response of certain metals or alloys or materials that you're using. So you can look at them individually. You can look at DIC and you can look at infrared imaging separately, or you can combine them. And something that you can do is you can overlay them, and then if you take away the thermal response from that, you can also achieve just strictly the mechanical strain of that sample. And this is something we're getting more into, and we see a pretty good benefit in doing both here. Okay, next we will move on to our new Radia series cameras. Okay, these are the Radia V60 and the Radia M100. We consider these to be more of like an accessible and ease of use scientific cameras. They're easy to integrate because of their low size, weight, and power. The Radia, which is the camera on the right in this image, is kind of your typical long wave camera where it fits in the palm of your hand. And the M100, the camera on the left, is maybe about twice that size. And that's more of your typical mid-wave camera. So the V60, like I mentioned, it's an uncooled microbolometer with a pixel array of 640 by 480. That can operate the highest at 60 hertz. It's got an 8 to 14 wave bandpass with a 12 micron pixel pitch, so you can still get some pretty high resolution. And we'll take a look at an example using the V60 in a second here. So this camera is a little more sensitive to thermal changes towards ambient temperatures. And we see this as more of a camera to use during quasi-static events or some slower rates or smaller speed tests. It comes with several different calibrations, as we can see here, high sensitivity, standard, and an extended, and then it can be calibrated to a high temperature thermography up to 1100 degrees Celsius. And the M100 is more of your typical cooled midwave camera in smaller format. Okay, it also has some pretty good resolution, spatial resolution with a 640 by 512 detector array and a 10 micron pixel pitch. It targets a little bit more of a specific 3.6 to 4.15 micrometer wavelength range. But something that's kind of unique to this camera is a standard calibration is from 0 to 850. We usually don't see that with mid-wave cameras. And it being a cool mid-wave camera, we're able to achieve some higher frame rates with it. And the calibration, of course, using telepsonic calibration, we can calibrate this camera up to 2500 degrees C. So we really see this as more of a high temperature, high strain rate application type camera. And if we're talking about integrating it with a multi-camera system, or if you have an experimental setup that involves some tight spaces, one of these two cameras could be very useful for that particular situation. Well, you could easily mount this on a rig, or if you have, if you're doing like a tensile test where you need to get up close and personal, and you don't have a lot of space, one of these low SWAT kind of smaller cameras might be of use for you. So at the V60, did some tests at Oxford University. This was done by my colleague, Antoine, another field application engineer here with us at Telops. These are a couple of examples. And we could see here there were two different tests. The test in this image on the left, A, and then a different test, the images B and C. And with the V60, we can see that it was able to pick up the X pattern at the onset of plasticity, and we're able to observe that asymmetry and the evolution of this band here on the right, the thicker band, kind of becoming the dominant band and overtaking. So eventually we start to see the thermal response and energy kind of diffuse into or into a lateral and then vertical movement originating from this dominant band here. And then if we look over the other two images, image B and C, we've drawn a line profile through this. This is another uniaxial tensile test. And we can look at the temperature profile of that line as the test evolves. Okay, we get a nice increase in thermal response from this localized nuclei here. And then again, we can follow that and look at the evolution of that and see how that changes over time and how it changes in the X direction as well. And then we can also notice that right before fracture, if we look at the line temperature plot down here, right before fracture, we get this spike, this peak in temperature. Kind of helps give us an indicator of when that fracture might occur. We're going to see that sharp increase and that sharp spike in temperature right before fracture happens. So we can see that the V60, this was a quasi static event, so slower speeds, but it was able to capture this thermal response during these testile tests pretty well, and still able to achieve some high spatial resolution for those tests. This was another test that was done where they measured 3D printed material with different percentages of a polyurethane and looked at the thermal response of that. This is an example with the highest at 60% of the polyurethane in the material. And as it's being compressed, we can see that there's an increase in the temperature. We see an increase in that thermal response as it continues on. This video, of course, is played back at a much higher speed than what the actual test was taken at. But we can see, if we look here in our charts, that as the compression occurs, we start to see the increase in temperature within the material. And we can see the maximum and the mean temperature increase over time. So what they're able to find is that with higher density of the polyurethane material has a greater thermal response. Okay, so more energy is being released in the higher density material. And with the lower density material, you have something that's a little bit more elastic. And then to mention here kind of the last camera that we'll mention because I recently heard a presentation where someone was talking about needing high dynamic range within material testing. So I wanted to mention here our high dynamic range camera. This is the HDRM 700. And so typically within a midwave camera, you only get maybe a couple hundred degrees of a temperature range within the same scene in a fixed exposure time. But with the HDR, like I'd mentioned earlier, we're able to see up to a 900 degrees Celsius in scene temperature range within a single exposure time, which is pretty phenomenal. And these two images down here on the right are of a firework, and we're able to see there's a pretty drastic difference between the dynamic range of the HDRM 700 and maybe more of a typical midwave camera. We're able to see a lot more distinct features. We've even seen greater than 900 degrees Celsius temperature difference in a single image as well. I think we've seen up to 1,000 before. Some examples of that, this on the left is a torch on steel. So we really get a sense of being able to see the super hot flames and also being able to see the background, the workbench that the flames are on, that the torches spray onto, and even the worker in the background at the same time. We're able to see these really hot temperatures of the torch itself. And this might be a little bit more relevant. This was an additive manufacturing example where we can see a laser kind of etching into this material here. Kind of, like the other video with the HDRM 700, we're able to see the background of this while also picking up the high temperature of the laser hitting the material and etching in these pieces. All right, that is enough for me on the teleops side of things. Hopefully that gives everybody kind of an intro, at least what we've done here at teleops Exosense with experimental mechanics and testing and how our infrared cameras can be used or are used for material tests. But I would like to now turn it over to our guest, Hossein. And give me 1 second. I would like to give you guys a brief bio. He is a PhD student in material science and engineering at Tampere University in Finland, currently studying the mechanical behavior of modern metals with complex microstructures using in situ high-speed techniques. He has a keen interest in exploring the mechanics of materials and microstructures through a combination of physics-based and data-driven approaches such as machine learning. And we are very excited to hear what he has to say today and what he's going to present on. The paper that we read was very interesting, and we're looking forward to the integration of everything that he did with this. So I'm going to give him permission to share a screen here. Make him the presenter, and all right, I was saying you should be able to share with us your screen.
Yes. Thank you, Chris, for inviting me to this webinar. And hello, everybody. I'm Hossein from Impact Group in Tampere University. Today, I will talk about the in situ characterization of high strain formability of metastable austenitic stainless steel. I will talk about a little bit about the background and motivation and the research question that we had in my PhD path. And I will talk about the factors that affect the creep effect, and I will compare the traditional and the modern measurements, and I will discuss the material and method and the experimental setup that we had at Synchdrome facility at Max for Lund, Sweden. And I will show you some example raw data, and I will show you FEM simulation, and at the end I will show you some result about the heat generation. Well, in this world, we need more material. It is because of global mega trends. We need for new energy sources. There is decreasing natural resources, so we need more materials. And therefore, we need for new technologies and improving the old solutions. We need to make materials with high performance and sustainability. So we develop some materials with high complexity and sophisticated macrostructures. These materials enables complex and sophisticated mechanical behavior. However, traditional methods are inadequate to predict the behavior of this mechanical behavior. So the importance of modern experimental research in this area. For example, in modern steels, there is solid-state martensitic phase transformation that happens during loading. This transformation increases the strength and ductility. For example, there is a trip steels in automotive industry that produce lighter vehicles because they reduce and also reduce the fuel efficiency and also decrease the carbon footprint. At the same time, they increase and enhance uh, the safety of the passengers because they have the high energy absorption capabilities. So, with this in mind, we took metastable austenitic stainless steel of 301 because it has, because of this trip effect, good mechanical properties. For example, you can see here under loading, the austenite-martensitic uh, grains transfer to martensite grains. So we need to know what parameters affect this trip effect because it's very complicated phenomena. We know that there are many parameters that affect this trip effect, like strain rate, temperature, and stress or strain state. For example, in this figure, with increasing the strain rate from 2 by 10 power of minus 4 to 1, you can see the positive strain rate sensitivity in the yield strength. However, after some point, it decreased, and it is because of the total transformation that with increasing from low strain rate to high strain rate, the volume fraction decrease. And also, we know with the thanks to the IR cameras, we know this phenomena because of the adiabatic heating and other parameters. And also, we wanted to know the in situ data about the simple shear because it's in the literature was rare. And also, our research question was that how we accurately predict these parameters under real scenario like sheet metal forming. So we took our samples, we took three kind of specimens to in situ synchron facility to test and to know the different parameters. In this slide, I want to show the traditional and the synchron XRT measurements and compare them. For example, in the traditional method, these dots are each one specimens. So for getting one curve, you need 10 loading experiments. You need interruption of the loading. You need to take your specimen and go to the microscopy center and do post characterization. So traditional methods are not optimal at all because you have interruption of loading. They are usually destructive and it is very time consuming. However, with synchron data, each of these graphs produced by one experiment, and one experiment gives you over 100 measurements during the loading. So you have real-time data, and it is very awesome. Also, this in situ data gives you bulk information compared to other measurements like TEM, EBSD, SEM that gives you information just about the surface. In situ data gives you the bulk measure and bulk information. And also in these measurements, we had the chance to go into high speeds, about 250 hertz. So we can um, use also these measurements in high speed uh, dynamic situation. And thanks to the built-in mechanical loading that supplemented with the IR and optical camera, we could get the high temporal resolution thanks to the synchronization of different instruments. So we could solve the multiphysics problem because every instrument was synchronized and we could get information from all instruments. So this data is real high resolution data. This is the most important slide in my presentation. You can see here, this is the inside the hatch in DanMAX beamline. It took us half a day to set up this experiment. And there are many challenges. For example, the challenges of the synchronization. You should synchronize the IR camera, optical, and the XRD detector, and also XRD, the incoming beam. You can see here the detector, the beam coming from through here, the optical camera and IR camera. So X-ray beam comes through here, hit the sample in the center in here, and detected by the detector. At the same time, the optical camera through the mirror inside here uh, record the pictures and record the displacement, and by calculating the displacement give you the strain. And also the optical IR camera measures the temperature. You can see here the loading device that it had two actuators that simultaneously move up and down, so the samples stay stationary and at the center. You can see here the plane strain specimens, and we had three kind of specimens to test the parameter of stress state on the phase transformation. And at figure 3, you can see the example of IR temperature measurements. So in this slide, I want to talk about a little bit infrared thermography. The camera we used was fast IR 2K. We used 50 millimeter lens, and this camera has the actuation rate up to 90k hertz, and the full pixel resolution was 320 by 256. Here you can see the sorry.
Real quick, Hussein, I think you might be muted. We're, we're unable to.
Can you see? Can you hear me?
Okay, yep, now, yep, we can hear you again.
Okay, sorry. Okay, before testing, we had the calibration on the IR temperature. We used thermocouple, as you can see in this figure. We mounted the thermocouple through spot welded, and we increased the specimen's temperature to almost 120 degrees and let the specimen cool down. At the same time, we measured the temperature of the specimen by thermocouple and IR camera, and through this figure we fit the linear or polynomial function to get the real surface temperature. But we had also uncertainty. For example, in higher uh, uh, at low temperature and high actuation rates, we had sensor noise, so it was our uncertainty. And also, there was thermal inertia of thermocouple that uh, caused a slight delay during rapid cooling. So also we had uncertainty, but the measurement was accurate because we uh, convert the IR radiometric temperature to surface temperature by this calibration. We had challenges during temperature measurements for simple shear specimens. As you can see here, we have very small gauge lengths, about for 4 millimeter in here and 1 millimeter width. So it has also the shadow itself. So it was not accurate. So we presume it's approximation. And as you can see here, there's some shadowing in here. Also, other challenges was the positioning of the IR camera. We had many cameras and instruments, so it was really difficult to go as close as possible to get high spatial resolution. So it was really challenging to know the best position of the IR camera. And also we had some shininess on the surface of the specimens, so it compromised our calibration accuracy. And these are challenges that we faced in our measurements. In this slide, you can see the example raw data of plane strain specimen at strain rate of 1. And as you can see, it took almost 1 second to perform and carried out. And it gives us many data, a huge data. For example, one test at a low strain rate gives you 40,000 frames, and it's really huge data. And this is the mechanical data that through this you can calculate the stress. This is the optical uh, pictures that through digital image correlation you can get the global strain. You put patterns on the specimen, and through the subsets that track by the algorithm in the digital image correlation, it gives you the displacement and the strain. And also with the IR camera, you measure the temperature of the surface in the gauge length. And we had also, in addition to this information, we had the diffraction measurements. Each of these rings are at different 2 theta. This is the transverse to loading direction, this axis, and this axis is the loading direction. So these directions are important to us. So we transformed XRD at Cartesian to polar coordinate. So we easily manipulate these data and cut this data to analyze. Diffraction measurements gives us the volume fraction of each phase. For example, you have austenite, martensite, or other phases. For example, in our test, we have also epsilon martensite. And also, you can calculate the texture. As you can see in this video, through each of these rings, you can see the higher intensity and lower intensity, and it gives you the texture. And also with the peak shifting, you can calculate the carbon content, and with the broadening of the peaks, you can calculate the dislocation density. Right now, I'm working on this topic, and I want to calculate the dislocation density accurately through these measurements. This slide also shows the raw data of a simple shear specimen at high strain rate, and as you can see, it gives also very high resolution data and of all instrument, optical, IR, mechanical, and also uh, diffraction data. Well, we had FEM simulation to has backup and also the validate our measurements. We used the thermo-mechanically coupled explicit dynamic simulation that included strain rate and temperature dependent continuum material model plus phase transformation of Olsen cone model. And as you can see here, these are example of stress and strain maps. And as you can see, in all gauge lengths, the distribution of stress and strain, these are strain and these are stress, are homogeneous. And we plot these figures of strain to show that in this center, we have the plane strain condition. So we had also a FEM simulation, and we compared with the real data. And in here, I just bring the data of temperature, and you can see other results in the paper. I will show the QR code, and you can scan that. Here, you can see the temperature heat generation generated versus effective strain, and these are the real temperature, and these are the numerical result. As you can see in the uniaxial and the plane strain, it is really predicted well, the FEM simulation. And as you can see here, the temperature throughout the gauge length is distributed homogeneously. But we had problem with the simple shear specimen that I discussed in the previous slides, and it gives underestimated the over predicted the temperature, and it was because of the challenges we faced in this specimen. And also we had some problem in the FEM simulation that with the revising of some parameters in the Olsen cone, we could solve this problem. This is the QR code to my paper that recently published, and if you are more interested you can scan and see the paper. Thank you very much, and if you have any questions, you can ask, and I'm happy to answer your question. Thank you.
Great. Thank you, Hussein, for such a great and interesting presentation,
Thank you.
especially using DIC, X-ray, and IR. I find that very fascinating. Okay, we'd
Thank
like
you very
to
much.
invite anybody who would like to ask a question. Go ahead and um, insert those into the question box. Jose, would you mind turning your camera back on if you're able to?
Yes, yes, yes.
Okay, there you go. Okay, I'm going to assign you a question here so that you can see it. You should be able to see it in the questions box. And for everybody,
Yeah.
the question is, are you using any commercial algorithm for DIC?
Yes, we use Davis, and that calculate our displacement and strain. If you know Davis program, there's a application named Davis that is commercial, and it is not open source, and it's actually makes our optical cameras, and we use that commercial application. And inside that this Davis, we have algorithm like sum of differential or relative to first, that these are the algorithm that track the subset um, from in each of the pictures. So yeah, we use commercial algorithm, let's say.
Okay, thank you. Thank you for that answer.
Thank you.
I'll throw another question your way. Uh, and this question is, are you able to see that question? The question is, did you use a window to protect the IR camera? And if so, did you use any specific calibration?
Actually, we didn't use anything to protect the IR camera. We were worried about the detector, X-ray detector. So we use something to protect the detector out of you know uh, dust or other materials that under the loading may be through. So we didn't use any protection in the IR camera, but we used in um, for detector, and we just did the calibration I talked in the slides. So we used the thermocouple, and at the same time we use both the IR camera and the thermocouple to uh, record the heating and cooling part, and after that it was our calibration. We had calibration on DIC also, but for IR we just record the temperature that we heated up, and also when it was cooling down.
Okay,
Thank you.
uh, let's see. We have another one here. Let me assign it to you. Should be able to see that now. And the question is there any significant impact of the DIC paint on the temperature measurements?
Yeah, actually, we tested both. We put the pattern on the DIC, and we didn't also put the pattern on the specimen. So we measured at the both case. So when we didn't use the pattern, the temperature accuracy was high. So uh, we calculated DIC with that patterns. Especially this pattern was significantly important in the high strain rate because it should track that patterns. So we put the patterns on high strain rate, and in low strain rate we make that unpatterned. So the accuracy of the temperature we wanted to get high, so we use both.
Okay, I know coming into this world of DIC that the paint and the speckle pattern, is very interesting, and the
Actually,
application of it and
when
effect
you
of it.
you don't have any choice, you can also pattern not just gauge lengths. You can pattern other parts, so it's not that accurate, but it gives you the global strain. If you're not interested in the local strain, for global strain it's okay, but for local it's a little bit not that accurate.
Okay, that's good to know.
Yes.
Okay, I'll send another one to you here. I'm kind of interested in this one as well. Um, did you
Okay.
spatially calibrate the DIC, IR, and XRD systems so that you could isolate the data from all three at a specific point? I know this has been done with DIC and infrared, but not sure how this would be done with XRD. And I'm interested in that too. It's like, are you able to take all three and isolate data from at one point from all three of them?
Actually, we calibrate one by one. For example, we calibrate the temperature data. We put the sample there and heated the specimen. So we record with the thermocouple and the IR camera. We also use the LAB6 for calibration of the instrumental broadening of the X-ray. And also for the DIC, we put some plates, calibration plates, and we rotated it and we calibrate the DIC camera, actually optical camera. So at the same time, no, we didn't do this, but we did separately. If I understand your question correctly.
Okay, yeah, yeah, yeah. It's said be, if you're able to take both DIC, IR, and XRD at a single point and say like, oh, this we get all three of these at the same point. What does that look like, or what does that show us?
Oh, I understand that. You mean full field data. For example, one point uh, correspond to X-ray, IR, and also a strain. You mean that?
Yeah,
Yes.
yeah.
Yeah, yeah. It cannot possible in that synchron facility. You have very less time, limited time. You have just 2 days. You cannot do such a extensive uh, fulfilled data. But in Tampere, we had that. We have fulfilled data. We take the images from the IR and also uh, optical camera, and we for example transform the Lagrange Eulerian coordinate to Lagrangian coordinate, and we calculate it both in the same global coordinate. So we know that, for example, this data point correspond to that position and also that temperature. But for X-ray, no, we haven't done.
Okay, is that something that would be very difficult to do or possible to do, or is it? Do you think that's
I don't really know, but
okay?
yeah, why not? But it's a
Yeah.
little bit difficult because of the limited time in the synchron.
Okay.
Maybe in the future we could do that. It's a good idea that you have the fulfilled information of three instrument. Right now we can do it optical and IR. We transform the coordinate to each other, and we know that they work. Actually, right now we have project that master students doing, and we are doing those, and also previously we done. But for X-ray, it's very interesting, and maybe in the future.
Okay. Yeah. Great. All right. We have time for one more. I will ask. What did Do you remember what the highest frame rate you tested was? Did you try and test that super high
Yes,
frame
we
rate
we up to 10. It was 10,
up
10
to?
per second.
Okay.
Uh, yeah, it was jump test, and we got few data points. It was difficult, but maybe with the uh, you know development of the new detectors, we could do high strain rate. But we tested at 10, and we gathered few data, but still usable data.
Okay. So I saw in your one slide you showed looked like you showed 250 hertz was what was used for the infrared
Yeah, yeah,
camera.
it is for a strain rate of 1.
Okay. Okay.
Yes, it is correspond to strain rate of 1. For a strain rate of 10, I think it was 1000 hertz, 500, I don't remember, but
Okay. So you guys
something
went up
like
there a little
this.
bit.
Yes.
Oh, nice. Awesome.
Thank
All
you.
right, everybody. That is all the time we have for today. There are other questions that we were unable to get to. And like I said, we will take all of the questions and provide written responses to those written questions and send that out in the follow-up email afterwards. So thank you everybody for joining us today. We
Thank
hope
you,
you
everybody.
found this session very informative and valuable. Thank you for the participation from the audience, but a special thank you to our presenter, Hossein. Thank you so much for sharing your
Thank
expertise
you
and
very much for
insights with
inviting
us.
me to this webinar.
Yeah, your PhD research, that's very interesting. If you have a chance, go out and read the paper. The contributions that you made to this webinar have been very engaging and insightful, and we appreciate you coming on and sharing that with us.
Thank you very
Um,
much.
it, and if anybody has any further inquiries, please feel free to reach out to us. Reach out to me. A recording of this session will be available soon, and we'll be sharing additional resources for any of those interested. If you see us out and about, we go to conferences and we do these webinars. We hope to see you there. And if you're out at a conference or anything and see us around, feel free, say hi, stop and say hi. We love talking about applications, and on the IR side, we love talking about infrared cameras and how they work within the applications. So thank you again, everybody, for being with us today. We look forward to seeing you at our future events, and have a great day.